In the first two sections of Chapter 7, we will start looking at the evidence that you find for chemical reactions. So let's get our pen here just in case we need it. So we've talked a little bit about that classic science fair project, the baking soda and vinegar volcano. And we talked about the fact that it's an endothermic reaction. It's actually a cold volcano. We know that it bubbles and fizzes. Well, what's happening is the baking soda, which is sodium hydrogen carbonate or bicarbonate, is reacting with the acetic acid in the vinegar, and it forms carbon dioxide gas, so that's the gas you see coming off, water, and then sodium acetate that still has that vinegary smell to it. So that newly formed carbon dioxide is what we see bubbling out of the mixture. That's what causes the volcano to erupt. Okay, that's the gas we're getting. And these reactions that occur in liquids and form gas are known as gas evolution reactions. So we're going to be looking at different types of reactions in this chapter. And then just red food coloring that we have that just helps us see the bubbles. So what is it that we have in here that's an evidence that a chemical reaction has taken place? Well, it's the evolution of that gas. All right, so let's look at another kind of reaction. Reactions that occur in our automobiles every time we drive somewhere. And these reactions are combustion reactions. So if we look at an auto engine, at what's going on inside, we've got things known as hydrocarbons. A hydrocarbon is just something that contains only hydrogen, well, not only, but hydrogen and carbon primarily. You can have some other things in there, but they're primarily made of hydrogen and carbon. Now, kind of the classic standard for a combustion engine is octane, which is 8 carbons and 18 hydrogens. Okay, so they've got it represented by this molecule up here, octane. Octane reacts with oxygen, okay, shown right here. So remember, oxygen is one of those that occurs as a diatomic molecule, 2 oxygen atoms, so an O2. These two react together in the automobile engine, and they produce carbon dioxide and water, both as gas, as water vapor. All right, so what is a combustion reaction? What is our evidence? Well, the evidence is that we no longer have octane and oxygen. We have 2 new gases. We have carbon dioxide and water vapor. And combustion reactions can be categorized. They're a subcategory of what we call oxidation reduction reactions or redox reactions, in which we're transferring electrons from one substance to another. And we're going to look at these different types of reactions as we go through the chapter. All right, another example that they talk about at the very beginning of this chapter is the chemical reactions that occur with a laundry detergent. So when we put our Tide or Biz or whatever we have into the water, what are we putting in there and how is it working? Well, the reason we use laundry detergent, and notice that, we're talking detergent here. Laundry detergent is going to work better than soap. Now, detergent and soap have very, very similar structures, but there's a slight change in the way they're put together that allows laundry detergent to have a property that soap does not have that gives it the advantage. And that is that if you put soap into water, depending on what kind of water, if you put soap into pure water, you can see here that it foams or it has suds on it. So we have these suds that have formed on the top of the beaker. But now if we take that same soap and we put it into what is known as hard water, which is what we have here in the Ozarks, hard water has ions dissolved in it. In particular, mostly calcium ions, that's calcium 2+, and then also some magnesium ions. These ions, calcium and magnesium, bind to the soap molecules that we have put in the water, and you'll notice no suds. That's the only difference between these two beakers. One has pure water, one has calcium and magnesium in it. Okay, so imagine, if you will, little calcium ions floating around in here, magnesium ions floating around in here. those ions, calcium and magnesium, are going to bind to the soap, and they're going to form this gray slimy substance that we call curd. You don't hear that too much, or the one you're more likely to hear is soap scum. Soap scum is nothing but precipitated soap that's reacted with these calcium and magnesium ions. Okay, so if you've ever had to wash your clothes with ordinary soap instead of detergent, you may notice that kind of gray scum or residue that builds up on there. It may have kind of a greasy feeling to it. This is why we use detergent. Okay, detergent doesn't have the same reaction. Laundry detergents are going to have things such as sodium carbonate in them. And let's see, did I lose my pointer? There we go. Okay, so sodium carbonate. The sodium carbonate helps to remove the calcium and magnesium ions, plus the detergent doesn't bind irreversibly to those ions. It works a little bit better that way. But what happens is the carbonate from the sodium carbonate, okay, so just the CO3 part, is going to react with the calcium ions and the magnesium ions. Okay, so calcium 2+ here, and we've got magnesium 2+ here, and then over here we've got carbonate, which is our polyatomic CO3 2-. CO3 2- can react with the calcium 2+ and the magnesium 2+ to form solid calcium carbonate, solid magnesium carbonate. Those can precipitate out. Okay, so by precipitate, they form a solid, they come out of solution, settle to the bottom. Okay, and so now those ions, magnesium and calcium, are no longer there to react with the, quote, soapy part of the detergent, the molecules that do the actual cleaning. Okay, so when we look at those type of reactions, that's another type of reaction. We call those precipitation reactions. Anything where we combine things that are dissolved in water and they form a solid or a precipitate. All right, so those are all different types of chemical reactions. And we've talked a little bit about physical properties and chemical properties. So we want to talk about what is the evidence that we see for a chemical reaction. How do we know it's a chemical reaction, not a physical reaction? Well, if we could see the atoms and molecules, if we could see them, that would be easy to tell. We would just say, well, did we have different compounds than we had to start with? Because in a chemical reaction, atoms are going to combine with other atoms to form compounds. New molecules are going to form. The original molecules tend to decompose. Okay. And then the atoms in one molecule may change places with the atoms in another. All these different things can happen. Okay, if we could see the atoms and molecules that make up matter, we could just look for the changes that we see, those types of changes. But we can't see atoms and molecules. We can't see if molecules are decomposing, new molecules are forming, if molecules or atoms within the molecules are trading places. What we have to look for are the macroscopic changes that occur because of the molecular changes. The macroscopic changes are things that are occurring, in the macro world at our level. So that's what we have to look for, those pieces of evidence that tell us something is going on. And what are those pieces of evidence? All right, so one thing we can look for is light given off. So a chemiluminescent reaction, fireflies, glowworms, glow sticks, anything like that. Is it emitting light? Okay, or is it emitting heat, or is it absorbing heat? Is it an exothermic or an endothermic reaction? That's an indication there's a chemical reaction occurring. We already talked about this one. The formation of a solid in a previously clear or uncloudy solution. Now what you have to watch for is formation of a precipitate. A lot of times people think by solid it's going to turn solid like a piece of metal or a piece of paper or something. It's not necessarily going to do that. The solid may just appear as a cloudiness in solution that settles out over time. So what we're looking for is a material appearing in a previously clear solution that creates an opaque appearance that prevents us from seeing through the solution any further. You may see evidence of a color change. So you may see a clear to pink, or you may see blue to yellow. You may see some sort of a color change occurring that indicates a chemical reaction. Or you might see when you, for instance, put a solid into water or another liquid, you may see the formation of a gas. Or you may pour two solutions together and see formation of a gas. We saw that in the lab with the chemical clue lab, the formation of carbon dioxide with the carbonate ion. So you've seen the evidence of all of these different chemical reactions in the various reactions we've seen in lab. So here we see a couple more pieces of evidence for chemical reactions, just a couple of visuals. If we look at the picture over here on the right, we can see precipitation reaction where a solid is forming. And so the red material that we see here is the solid forming in the previously clear solution upon the addition of this solution from a dropper. So you can see that the solution in the dropper had a yellow color to it. The solution in the test tube is sort of a clear color, but when we mix them, we get this red solid. Okay. And then if we look at the one on the left, this is a gas formation reaction. We've dropped an Alka-Seltzer tablet into water, and we can see the bubbling and fizzing that are occurring. Formation of the gas is giving us evidence that a chemical reaction is occurring as that Alka-Seltzer tablet dissolves in the water. Now we have to be careful because sometimes we see things that may mimic what we've just talked about that seem to be evidence of a chemical reaction, but they're not. So for example, if we have water boiling, we've got bubbles forming, there's a gas evolving, but we don't call that a chemical reaction. No chemical reaction has occurred. That is simply the evidence of the water changing from a liquid state to a gas. So we're going from a liquid to a gas, and that is the gas we're seeing. That's simply a physical change. So water and steam are the same chemical compound. No chemical change has occurred, just a physical change. So we have to be careful and really know why something is happening, why it's occurring, and look at, is it coming from, nothing's changed about the situation except we've mixed two things together, or has heat been applied to this situation? And that's different from a reaction that generates its own heat. This one has had heat applied to it. All right, so we've already said that it's the changes that occur at the atomic and or molecular level that tell us whether or not a chemical reaction has occurred, but only chemical analysis that shows that the initial substances have changed into a new substance will prove conclusively that we have a chemical change. So we have to look for a chemical analysis in here. Now, a chemical analysis doesn't have to be anything that complicated. We just have to analyze or look at the makeup of what we're starting with and what we're ending with after any sort of reaction. Sometimes a chemical reaction may occur without any obvious signs. We may not see the things that we've talked about here, but chemical analysis would indicate to us that something has really occurred. And it's the changes that are occurring on the atomic or molecular level that determine to us whether or not a chemical reaction takes place. So even though we can use evidence at the macroscopic level to tell us what's going on, we have to realize that sometimes we have to verify that at the microscopic level. All right, so that's just a summary of what we're looking at in the first couple of sections of Chapter 7 here. We just want to get across the idea that we want to look at types of chemical reactions and learn how to recognize a chemical change when we see one. Now we want to start looking at how to interpret that and how to write and read chemical equations. We'll look at that in the next two sections.